right, welcome guys. Completing the square, day 2. Yeah, this is the very last day of chapter 8. It's actually just a continuation of the same section from yesterday, 8.2.5, completing the square. In this video, I do all of this with you guys. This sheet of paper is pretty much blank at the beginning, and then I spend almost a half hour just kind of going through the whole thing, okay? So if you really don't want to spend a whole half hour on this, you can skip the very last question. I think it's a good question because it gets you thinking about coming up with formulas, and we'll be coming up on something called the Quadratic Formula in just a few more classes. So doing this last question is helpful for that. But it is a long part of this video and not terribly important. The key thing is, by the end of this video, hopefully you get really, really good at going from standard form to vertex form, and you realize exactly everything you need to do. It really is just 3 steps, okay? So I try to break that down. In all these problems, you're doing the same 3 steps to go from standard form to vertex form. And that's it. Good luck. All right, everybody, this is part 2 of completing the square. I'm excited to do this one because I haven't done a lot of it so far. Notice here, my paper is pretty blank and it's completely blank on the second page. So I'm gonna do a lot of it along with you in case you had trouble going through it the first time. Or maybe you're just doing along with me today. Okay, so in a lot of these, this one here, and the ones in the back, what we're trying to do, reminders, completing the square is changing something from the standard form, right? Changing something from the standard form to its vertex form. And this is possible for a lot of quadratics. So how do we change that? Change it to its vertex graphing form here. So how do we introduce a perfect square somewhere to that quadratic and get that perfect square part factor, and then you usually have a constant out there. So that's going to tell you the vertex. Okay, so we're going to follow these steps, and hopefully that makes sense, and you'll get good and be able to do these very quickly going forward. All right, so we have Jessica. What's up, Jessica? We're going to help Jessica with a new problem. She needs to complete the square and write y equals x squared plus 4x plus 9 in graphing form. So the first step of what to do is you need to figure out what your perfect square is going to end up being in the vertex form, okay? So I'm gonna take my tiles and I'm just gonna do this with a generic rectangle this time because that's faster than actually drawing the tiles out. So I have my x squared piece right here. So if I'm gonna make this a square, my base needs to be the same distance as my height. They need to be the same dimensions. Remember, a square has 4 equal sides. So if I'm gonna take my 4 x's right here and I'm gonna lay them out over here, and lay them out up here. Remember, your x's go in this diagonal right here. I'm going to have to break it apart. I'm going to have to take 1/2 of x's, right, to each corner of the square because I'm trying to set up equal width to its height. So I'm going to do 2x here, and I'm going to do 2x here. Okay, so this means our perfect square that we're trying to create in this situation is going to be x plus 2 times x plus 2, otherwise known as x plus 2 squared, the quantity x plus 2 squared. Okay, so here's where the problem is. We have 9 ones right here, but what does it need to be, right? What do we need to get to? So we have 9 right now. What we need to get to is 4. We need to get to 4. So we have 9, we need to get to 4. So what are we going to do? We're going to, step 1, subtract 5 from both sides of equals. So I'm going to do that. I'll just do all the work out so we see a full example together. So I have y equals x squared plus 4x plus 9. And I'm going to subtract 5 from both sides. Minus 5, minus 5. I get y minus 5 on my left side. And on my right side, I get x squared plus 4x plus 4. That is, my friends, is a perfect square. So what we see here in the generic rectangle, we see x squared plus 4x plus 4. That can be written as a sum, also can be written as a product, x plus 2 times x plus 2. So I'm going to rewrite that as a product. So the right side here, I'm going to write this in an equivalent way. I'm going to write it as a perfect square, x plus 2 squared. And this equals y minus 5. So step 2 is kind of, I'm just going to do this kind of in a messy way for notes. Step 2 is to factor. Okay, we subtracted 5 from both sides of equals. We factor because we know we can write this in terms of its factors. And in step 3 is just going to be add 5. We're going to add 5 to both sides. And we will be done at that point. We add 5 here to the left side, and then we're going to add it to the right side because, again, the factored form has y isolated here. It's not going to be in factored form until y is isolated here, and then you have your perfect square, and then also another constant here on the right side. If you're adding something that's not 0, you'll see a constant there. So we'll add 5 to both sides, and we'll get this written out in vertex form. We've completed the square, and we've rewritten in vertex form. So that's sort of the complete the square part. What came right before this, and writing in vertex form is just isolating y at the end. And we got this written in vertex form. And that's going to help us graph it, which we're going to get to in parts B and C. Find the vertex. Well, we have the vertex right here. We just got to take -2 because, again, we need to make this parentheses 0 to get our minimum point here. Would be at -2. We plug in -2 for x. That's going to cancel this out to 0. And then 5 is going to be our minimum height of that parabola. -2, 5 is going to be the vertex. And the x-intercepts. Okay, so let's solve for the x-intercepts because something interesting is going to happen here. It says, what happened? What does that mean? So we'll try to figure this out in a second. So I'm going to solve for my x-intercepts. Remember, the x-intercepts, the value of x when y equals 0. So I'm going to put 0 here. And then I'm going to try to figure out what x is. X plus 2 squared plus 5. So remember, we have this one way of solving for x-intercepts when we're written in vertex form, and that's number 4. I haven't filled this in yet. We'll have another video later, but this was a lesson a few days ago, which was solving by taking the square root. So let's do that now. And the way we can do this here is we're going to solve by taking the square root. So we need to isolate this perfect square on the right side. So I'm going to subtract 5 from both sides. And then I'm going to get -5 equals x plus 2 squared. Next step, we have a perfect square here. I guess we need to take the square root of that side too. And let's do it. Let's introduce a square root symbol. Again, don't forget your plus minus over here on the left side. Remember, there are 2 numbers that could be squared to get to this. And I'll do my square root over here, which will cancel out the squaring. Okay, so here, let me put this over here. So plus or minus square root of 5 equals, well, that squaring here got canceled by the square root, so I'm just going to write x plus 2. And, oops, I missed the negative symbol. So what do we notice here? What happened? What does this mean? Well, it looks like we violated a rule that we have in math right now. And if we logic through this, you'll understand why this is a rule. Well, what do we see here? What do we see there? Is that allowed? No, that's not allowed right now. So we have a square root with a negative on the inside. So remember, any positive number is going to have 2 real square roots. Positive 4 has 2 and -2 as a square root. Positive 3, it's about 1.7 or so. Positive 1.7, negative 1.7 or so, that would be the square root, the 2 square roots of 3. Okay, so a positive number has 2 real square roots because a number times itself is a positive number. So you take a number, you multiply it to itself, you get a positive number as an answer. Remember, a negative number does not have a square root because you can't take any, there are no real numbers that when multiplied to themselves is a negative number. So for in this situation here, this means there is no solution to this situation. We can't actually figure out x here. So if you did this one and you actually graphed it out on the graphing calculator, you noticed you still had a parabola, right? We still have a parabola in this situation, right? We're graphing this is the original equation right there. We still have a parabola, but when we tried to solve for x, we didn't get an answer. And what do we notice about this parabola? Does it have x-intercepts? There are no x-intercepts. Our parabola's minimum point here, again, we know the vertex, it's -2, 5. It's above the x-axis. Here, this 5 is positive, so it's above the x-axis. So our lowest point is above the x-axis. We actually don't hit the x-axis. So this one here is no solution. And technically, and we're going to see this later, we're going to say that these no solution parabola does not hit x-axis. And another thing that we can say about this is that it's not going to have real roots, right? Real x-intercepts. So the roots here, remember, if we are solving by taking the square root and we have a square root symbol, in the end, that would normally mean the roots are irrational. They're not really clean numbers. They're non-terminating, non-repeating numbers. So the answer here isn't that the roots are irrational numbers. The roots are imaginary numbers. So I'm going to write this here, imaginary roots. And that'll be something you'll be studying in a whole bunch of advanced math classes, is if you're going to solve for the roots of a particular function, a particular equation, you might end up with imaginary roots that you're finding. All right, so the last question is algebraically find the y-intercept and sketch its graph. Well, if the x-intercepts are the values of x when y equals 0, of course the y-intercept is the value of y when x equals 0. So we'll plug 0 into the original equation in standard form, which is kind of doing too much work because, remember, that constant term that appears at the end, that's just going to be your y-intercept. 0 squared is 0, 4 times 0 is 0, so 0 plus 9. Y is going to equal 9. Our y-intercept is 0, 9. Okay, so we have our y-intercept. We have our vertex up here in part B. Remember, those are two key features. That's enough to sketch a parabola. And I'm going to do that now. So remember, this isn't quite as good as actually having roots to sketch it out. You can usually sketch it a little bit more cleanly. But it's enough to actually sketch out if you just have the y-intercept and vertex, because you can just graph half of the parabola. You should know kind of what parabolas look like at this point in time. So this is just half of the parabola. Remember, parabolas have symmetry. So we graph this, we'd have a line of symmetry right here. You're just looking for the mirror image on the left side. I'm trying to make it a little bit more curved because I don't want to make it look like an absolute value graph, too V-shaped. It should be U-shaped. And there we have a sketch and we're good to go. All right, next question. We have here, how could you complete the square to change this function, f of x equals x squared plus 5x plus 2 into graphing form? How would you split 5 x tiles into 2 equal parts? So hopefully you read this one. I'm not going to spend a ton of time on this one because I'm hoping you read it and kind of understood. But maybe if we can just do this with a generic rectangle instead. What it's just getting at here is that you might have fractional answers. You might have non-whole number answers here. So if you're creating a square, you can still create a square even if you haven't here. The big thing is that the amount of x's you have are an odd number. It's okay. It's okay if this is an odd number. You can actually still find a perfect square. Let's do it together. So what Jessica decided to do, she used force, right? She used force. Remember we have those tiles here? We don't have chainsaws in class, so we can't actually like cut those tiles in half, but I'm guessing Jessica might have one at home, and that's what she did. She stayed very careful not to chop off any fingers, but she chopped it apart. She had the 5x's here. So the only way we have with 5x's to set up an actual square is to break it in half, and half of 5 is 2.5. 5 divided by 2 would be 2.5. So if we break it in half, we would have 2.5 x's here and 2.5 x's on top. And then the perfect square that we're trying to create is going to be x plus 2.5 times by x plus 2.5. So she has 2 1s. So this isn't a perfect square. She's just kind of setting it all up right now. She has her 2.5 x's here, 2.5 x's here. She has 2 1s. She still has a little bit more to fill in for this perfect square. Okay, and the way you can figure that out, what she needs to get to, what are the 2 numbers you need to multiply together to figure out how you complete that square? Let's look at it over here. What are the 2 numbers I need to multiply together to figure out what I need up here to complete my square? Well, 2.5 and 2.5. So kind of what goes here is going to be what we need to do to get to complete the square. We need to square whatever number is here. Okay, number is here. That's how we figure that out. So you can do that in a calculator. I mean, you can do it in your head. You can change it to a fraction. That might be one way to do it. One way I could do that in my head is if I change that to a fraction, right? This would be 5 over 2 squared. So the square of this would, if it's 5 over 2 squared, the square of this would be 25 over 4. And 25 divided by 4 is 6.25. Or I can just do it in my calculator, right? I can do 2.5 and I can square it in my squaring button, and I get 6.25. Okay, so what we need to get to is 6.25. We only have 2, need to get 6.25. I think you guys know what to do. you just need to add 4.25, right? Because 6.25 minus 2 is 4.25. You just need to add 4.25 to both sides. If we're going to complete this square, we get y plus 4.25 equals, and I'm just going to skip over this here. I'm going to factor it together. So, because we know that the whole goal of this, if we have 6.25 over here now, is to get to x plus 2.5 squared. Last step to completing the square, or actually writing in vertex form, we've already completed the square here, is to subtract that 4.25 back from both sides. So we get y equals x plus 2.5 squared minus 4.25. And that's it in graphing form. So how many small unit tiles are missing from Jessica's square? It was 4.25. And it says, write the graphing form. We have that up there. Name the vertex. That would be negative 2.5, negative 4.25. And the y-intercept, I get that from standard form, so 0, 2. And sketch the graph. This is going to be messy down here, but that's okay. Sketch the graph here. Super sketchy, messy sketch. So we're going to be at negative 2.5, 1, 2, 3, 4, negative 4.25, 1, 2, 3, 4, 5. So about here would be one of the points, the vertex, and then the y-intercept was at 0, 2. Something like this. Quick sketch. And we have that parabola. Good to go. All right, let's wrap this up. I'm going on a little bit longer than I expected to, because this is not the longest of assignments. So let's do these together. Do this nice and quick. Write each function in graphing form and then state the vertex, y-intercept of each parabola. Okay, maybe I'll actually start by stating the y-intercepts, because we have these in standard form. So y-intercept of this one is going to be at, well, we need to find our C value. We have our A value is 1, B value is 10. That must mean our C value is 0. So our y-intercept is actually going to be a root 2, because it's going to pass through the origin. This here, we just plus 0 right here. So our y-intercept is at 0, 0. Here, it's going to be at 0, 2. All right, that was the easy part. We need to get the vertex, so that means we need to complete the square right in graphing form. So here, first step, we need to figure out what we need to do to add to both sides. That I would do with a generic rectangle, so x squared. And we have 10 x's here, so I'm going to break it apart. 5x over here and 5x on this corner here. Okay, one shortcut you're going to have here to figure out what you're going to need to get to your constant term to. Remember, the diagonals multiply to each other. So we have 5x times 5x. Would get us to 25x squared. So here, this would have to be 25 up here. So the perfect square we're trying to get to would be x plus 5 squared. So what we need to do is we need to, because we have 0 here and we're trying to get to 25, we need to add 25 to both sides. Let's do it right now. Plus 25. Plus 25. And again, this is f of x. That's fancy. I'm going to change it to not fancy. I'm going to change it to y. So 25 plus y equal to x squared plus 10x plus 25. Going to factor now. And y plus 25 equals x plus 5 squared. And finally, I'm going to subtract this 25 to move it to the right side. And we'll get it written in vertex form. Vertex would then have to be at -5, -25. And does it say sketch? It doesn't say sketch. So we have the vertex, we have the graphing form, and we have the y-intercept. And those are the 3 things the question asks for. Part B. Well, this was a tricky one here because we notice here our b here was even. It was 10, so we're able to divide that by 2, put 5 of our x's there, 5 of our x's there. This was kind of a little bit more elegant than this is going to be because we have an odd number for our b. So if we're going to set up our square that we're trying to complete on the right side, we have our x squared but we have 7 x's, so we're going to need to divide that by 2. That's going to be 3.5x here, and then 3.5x here. So the perfect square we're trying to get to, and I'm going to need to do this on my calculator, I'll be honest here. 3.5, probably could have thought through it really quickly and gotten it, but I'll just do it in my calculator. 3.5 squared is 12.25, because the perfect square we're trying to get to is this, x plus 3.5 squared. So that means our constant here is going to be 12.25, what we're trying to get to. This is 2. We have 2 ones. We need at least 10 more. We need 10.25 more on both sides. So I'm going to go ahead and I'm going to add that. I'm going to add 10.25 to the left side and to the right side so that I have a perfect square trinomial on the left side of this equation. Y plus 10.25 equal to x squared plus 7x plus 12.25. That is a perfect square trinomial. I know that because I have my perfect square right here. This is a sum, this as a product. So I'm going to rewrite the right side as a product, as its perfect square is shown with this binomial being squared. Y plus 10.25. Subtract this. Now we have to move it on back, right? 10.25. Like the whole idea is we made this bigger temporarily, right? We made this bigger temporarily, made that bigger temporarily too, but we want to get this bigger temporarily just to get a perfect square. Then we need to make it smaller again. We need to take this 10.25 away on the right side so that we have that perfect square hanging out on its own, and then we have a number making it smaller so that we get to the vertex, the true vertex of that original parabola. And it is the same parabola at the end. Vertex form, I already have my y-intercept, and I can write my vertex. There we go, that's B. All right, and finally, 8105 generalization challenge. So this was a little bit of a challenge where the idea is we have a quadratic written in a standard form. So after you do this a bunch, if you want to keep reasoning through it like this, I recommend, in fact, everybody, 100% of you, just reason through it, these problems like this, through this. Don't take any shortcuts beyond this. But you might be thinking, hey, do I really need to do the same steps again and again and again? Do I need to complete the square and follow those logic steps again and again and again if I'm just rewriting this into that, right? Is there an easier way? Is there kind of a formula that I can follow where if I have something written in standard form like this, and these numbers didn't really matter in these problems. We followed the same exact steps on both of these and both of the ones on the front. We figured out, we broke the x's in half, the amount of x's in half, and then we multiplied these two together to figure out what we need to get in the top right corner. And then we added or subtracted from both sides, whatever it took to get to that number right here. So what mathematicians typically do is, they'll look at real numbers, they'll look at actual examples like this and start figuring out how to solve them using the rules and laws of mathematics. And once they figure out and solving them, they try to figure out, okay, so what's a rule? Like what's something that we can follow to do this faster and more quickly in the future? So this is kind of an example of this. We have this written out in a generic form right now. Notice here we don't have an A in front. We're not actually going to have any A's other than 1 whenever we're completing the square. So just wanted to point that out. There going to be in Algebra 2, you'll study completing the square where A is not 1. So there'll be a few more steps you'll have to take. So what you do in Algebra 1 is you figure out how to complete the square when A is 1. So your first term is guaranteed to be a perfect square because x squared is a perfect square. So it doesn't really matter what your B is, doesn't really matter what your C is. You kind of follow the same rules regardless of how you solve these. So let's see if we can generalize a specific rule in the way to solve this. So I haven't done this one yet, so let's see if I can kind of do it. Well, here I have this written in a generic form like this. What I know, first step, is that I have to complete the square. So I'm going to set this up. And if I were to complete the square, this width here, right, if this is going to be x times x, it gets us to x squared. But our width here, we need 1/2 of our b's on this side of x squared, and then 1/2 of our b's above this part of x squared, so that we have the same height 1/2 bx. This has to be, yeah, 1/2 bx. The same height as we have width. So this is the perfect square that you're always setting up. You take a half of your b's, So half of our b's here was 5, right? Half of the b there was 5 because our b was 10. So we take half the b, half the b coefficient, and put it here for part of the width and part of the height. And so we have the same width and same height. Okay? So we have C1s over here. But what we're trying to get to, remember, you just have to multiply this times this together to figure out what goes in this corner. So 1/2 times 1/2 is actually 1/4. And b times b is b squared. That's what you get to up here, okay? So in this one here, b squared was 100, and a quarter of that is 25. Interesting, okay? So I haven't actually done this problem before, but that would be kind of the pattern to follow from this. So now what we need to do in order to get to that in this equation, so notice here in this corner, there is no c. The width and height has nothing to do with whatever your constant is here. Whenever you're filling out your square, it doesn't really, you're not thinking about what your constant is currently, because even though it's c now, what you need to do is you need to get it to a quarter b squared, right? You needed to get it to 25 here. It didn't matter if this was 0, it didn't matter if this was 2, you needed to get it to 12.25. So this will be a little messier than how, at least proving this will be a little bit messier than how you've done it above. So in this example here, what you need to do is we need this to be a quarter b squared and not c over here. So first step, you could get rid of the c. So I'm going to subtract c from both sides. And I'm going to get y minus c equals to x squared plus bx. And that's good because bx is, if we have a half bx here and a half bx here, that's a full bx. We do want that. We don't have a quarter bx over here as our constant term right now. So what I'm going to do is I'm going to add 1/4 b squared to both sides. Remember, even though this is a variable, as long as we add equal quantities to one side of an equal sign, an equation, and the same quantity to the other side of the equation stays balanced, and we know that the two sides would still equal each other. So here I have y minus c plus 1/4 b squared, and that equals x squared plus bx plus 1/4 b squared. This here is now our perfect square, what we just proved here, that all this funkiness here that we have here, that is simply the width x plus 1/2 b times height x plus 1/2 b. And so we can factor this right side and get it into a perfect square, and get it close to graphing form. This is a sum, that is a product. And we still have all this goodness on the left side of the equation. Wrapping this up, we have our perfect square right here, okay? We need to move all this information back to the right side, and then we have this written in graphing form. Y equals, and to do that, we need to, if we have negative c, we're going to add c to both sides. And if we have positive 1/4 b squared, I'm going to subtract 1/4 b squared from both sides. And we have this written as x plus 1/2 b squared plus c minus 1/4 b squared. And that is our graphing form here in generic form. So, are you going to remember this formula? No, you're not going to remember it. So don't do this. I would keep logic through them like this whenever we have completing the square problems in the future. So you could look at this and kind of think, well, where did this all come from? Like, I think I kind of get it now. So for instance, this was, in this equation here, we needed our C to be 12.20, or sorry, our C here was already at 2. We needed our sweet C to be 12.25. So we needed to take C and we needed to subtract that from the outside. Yeah, if you take C and you subtract the 12.25, you would get what would be the Y value of your vertex right here on this side. So this here, if you did follow it, and you knew this in standard form like this, you could just use this formula, plugging in what you know about B and what you know about C to this formula to immediately go from standard form to vertex form. Are you going to do that? Are you going to remember that formula? No, you're not. I wouldn't use this, but I wanted to point this out because this is what mathematicians do. They try to find out formulas where, hey, I don't have to do these calculations every single time, because I know that that this is the rule, that if I had something in this form, I can get it in this form right away. So this is going to be similar to when we do the quadratic formula coming pretty soon. Quadratic formula is just like that, where it's actually kind of complicated to see where the quadratic formula comes from, but the quadratic formula allows you to solve for x-intercepts just by knowing a quadratic, if it's in kind of this formula in standard form. Also, if the A is not 1, the quadratic formula works too. You can take those numbers here and plug them into a formula like this, and it's going to tell you the answer. So just so you have this as an example, maybe we can take, we can just do this one to double check that you could have just used this as a formula to get the vertex form. So in this situation here, our A is 1, that's good. Our B was 7, so let's plug it in just to see if we get the same thing. Y equals X plus 1/2 of B, and 1/2 of 7 would be 3.5 squared, and plus C, well, C is currently 2, and then subtract 1/4 B squared. So B squared, 7 squared, is 49, and 49 divided by 4 is 12.25. So we subtract 12.25, and yes, this formula would have worked if we knew it. This would have been a faster way. So 2 minus 12.25 is negative 10.25. This would have been a faster way to get to vertex form because we proved it already. And right, if you're following the same steps again and again and again, there's usually a formula you can use. So this challenge problem was just to get you to understand that there is this formula that exists. All right, that is part 2 of completing the square. Hopefully you guys get this process now. If not, this will be the very first lesson when we start chapter 9. Thanks again, guys, for watching the video. We can go over this tomorrow if you guys like.